Okay. So yeah. Oh yeah, this is recording right now. So yeah, any specifics of the exam? Does anybody have questions? I mean, it's just going to be the same as exam 1. So if you guys had trouble, now's your time to.
Hey, Jonathan, I wanted to clear something up with them actually real quick. Because or with you guys actually, because I just want to make sure, like, for myself and for everybody here. So I've been getting a lot of questions whether it's going to cover modules 4, 5, and 6. Because I've been looking at the reviews, and honestly, I think he meant, because he's been saying in lectures, been saying study questions 4, 5, and 6. I don't think he necessarily means modules 4, 5, and 6. I think what are being covered in those study questions 4, 5, and 6 are modules 3, 4, and 5.
Yeah.
And so I just want to clear that up before I say to the class, actually, to the students, what's being covered is modules 3, 4, and 5, right?
Correct.
Yeah. Okay.
Oh, and also atomic structure.
And atomic structure, yes.
So
yeah. Clarification.
On the exam. And you all should be attending lectures anyway, so you know, it is what it is.
Yeah. Yeah, what Jonathan said.
Cool. So yes, we could just start from the top and work our way down with the first questions. So let's do this. Wait, I need to re-look at the question real quick. Pressing buttons. So you decide to use the Liebig method to analyze this compound, and you find that 10 grams of the compound produces 14.2 grams of carbon dioxide and 8.71 grams of water. What is the percent composition of this compound? So, in order to figure out the percent composition, all you do, well, for starters, let's see. So we have carbon dioxide, right? Okay, find that 10 grams. We have 14.
Wait, what question are you doing really quick?
I'm sorry?
What question are you doing?
Oh, it was a question that someone put in the chat.
Oh,
Margot Ito. Ito. Does everyone know what I'm doing? I guess I should ask before I continue. All right, so we're gonna start with this question first. So in order to find the percent composition, we'll start with what's given to us, which is the 14.2 grams of carbon dioxide, the 8.71 grams of water, and then we have 10 grams of this given compound, which, because I don't know, I'm a math nerd, I usually call compound X. So with all this in mind, I'm trying to think of the proper way to tackle this. So we know what the molar mass is for carbon dioxide, right? And we can find the molar mass for carbon dioxide and the molar mass for water. So, and the reason why we're trying to find the molar mass for each of these is because, give me a second, I need to think before I start speaking. Anyone else can also chime in.
Here, Jeremiah, I kind of want to butt in here since we know that our products are carbon dioxide and water, we can assume that this is a combustion reaction with an alkane and oxygen. Mm-hmm. So we can start by assuming that it's asking us the compound is maybe an alkane, trying to figure that one out.
Mm-hmm. So we can put it Is this what you're saying? And being the amount of mole, because you can just multiply that to either C or H. All right, so
Okay, well, I'm gonna have a crack at this, if you don't mind. Okay, so first off, what we can do is we can convert these grams to moles, like straight up. So if you have 14.2 grams of CO2, how many moles do we have?
are you asking me or are you asking the audience?
Oh, the audience, of course.
Just so you guys know, you need to find the molar mass first. So you're going to be adding the weight of carbon by the weight of the oxygen.
All right, guys, we got 72 participants. All right, thank you. So 44.1 grams per mole. That looks like CO2. Yeah, so that means how many moles do we have? What would we do to find the moles? All right, 0.32. 0.32. All right, and then how many moles of H2O do we have? 0.48, right? 0.48 H2Os. So that means most likely this is a decomposition reaction, as they said, and most likely we are going to be trying to find an alkane. So that means how many, if I have 0.32 moles of carbon dioxide, how many moles of carbon do I have? Right, and then we're trying to find an alkane most likely. So that's, we're just trying to find how many moles of carbon and how many moles of hydrogen. Okay. Okay, cool. So that's a 1-to-1 ratio, right? So if we got 0.32 moles of carbon dioxide, means we got 0.32 moles of carbon. And same case with this, if that's 0.48 moles of water, that means we have 0.96 moles of water as well. Right. So if we got 0.32 moles of carbon and 0.96 moles of hydrogen, that means our empirical formula, we can try to do something with empirical formulas, right? So the way we find empirical formulas is we divide by the smallest. Again, divide by the smallest. And that looks, roughly 1-to-3 ratio. So CH3, that's our empirical formula, correct? And from the empirical formula, we can find our percent composition, right? Because, we have the empirical formula and we can just go straight to percent composition. Now, can somebody tell me how to do that? And then also unmute your mic. It's a lot easier for all of us, so we're just not waiting in the silence.
Multiply
Sorry, continue.
You would multiply the actual yields over the theoretical yields, and then multiply that by 100%.
Good. That's I'm blinking out.
That's percent yield.
Percent yield, yeah.
I also see something from Margot Ito. Okay, so where did I get the 0.96? Well, okay. H2O, we have 0.48 moles, right, of H2O. And we can see from the formula, for every one compound of H2O, we have 2 moles of H. So that means we would just multiply that by 2, getting us 0.96. You understand where I got that from? Yeah. Okay. So
Wait, you multiply
this is,
Wait,
you multiply 0.48 times 2?
yes.
Okay.
Yeah, cool. So we are looking for percent composition. And again, think about what the word means, percent composition, right? So that means we're gonna have to try to find something that's a percentage of a whole. So if this is our whole, this is our 100%, if you will. What is the percent composition of carbon? Right? And when we're talking about percent composition, we're talking about mass. So I'm trying to be as vague as possible. Bear with me here, bear with me here, right? So number one step we want to do, try to find the mass of that. And try to find the mass of the carbon and the mass of the hydrogen separately so we can see the percent composition. Right. So yeah, we would try to, not necessarily, we would try to find the total mass of this, right? So each carbon weighs 12, each hydrogen weighs 1, and then times 3, that's 3. So 12 plus 3, that's 15, right? That's our total. Our total is 15. 15 is equal to 100%. And let's just set up a mini proportion down here at the bottom. Jeremiah, do you mind if I erase this?
go for it.
All right. Just kidding. Can't erase that. So if 15 is our 100%, then our 12 is our X. You know, try to solve that. Just cross multiply, then divide. You know, so
Does that work?
carbon makes up 80%. Yeah, thank you. Carbon makes up 80% of the whole compound, and hydrogen will make up 20% of that whole compound. The way I got that is, you know, our whole compound weighs 15 AMU, 15 grams per mole. That's our 100%. And if each carbon contributes 12 grams for that, what is our thing? And the same thing with the other side, 15, 100, and then 3 hydrogens. How much does that make up? And then this would be your percentage, and it's looking like that's an 80, 20%. Everybody understand where I got that? Cool.
Is there anyone that's confused as to why he did it the way he did?
Okay, well, let's look at the study questions.
Oh, what's it called? I was gonna say earlier, but for the hydrogen, since it's still a 1-to-1, the amount of hydrogens on both sides of the equation, you didn't need to multiply by 2.
Oh, my bad.
No, you're fine. I was still trying to wrap my head around it real quick.
So what he's saying, all right, Jeremiah, do you want to explain what you're trying to say?
Sure. So basically, remember when everyone multiplied the number of hydrogens he had by 2 because there's a 2 subscript for the water? Like how there was a 1-to-1 for the number of carbons and carbon dioxide, as well as the number of carbons in the alkane that we were looking at. There's also a 1-to-1 and the number of, well, there's also a 1-to-1 for the number of hydrogens on the right side as well as on the left side. So, the only thing is that there's a 2 in front of the water. So this right here, the 0.48, that's the amount of moles there are of water. So if we were to convert it to the alkane that we had, we would need to divide by 2, not multiply by 2. That way we get the amount of moles that there should be for the alkane from the water. Does that make sense? Or did I like lose everyone just now?
Again, which study question is this? I want to go kind of look
Yeah,
look for it
also
myself.
like to-
All right, perfect.
Oh, actually, set 5 has a lot of fun ones, if you will. You know. How many of you guys understood question 8, number A, for set 5? So the reason why you guys probably didn't get 8A is because you haven't learned that yet, which is why I'm kind of confused why it's in the study questions.
Yeah, I was gonna mention that. I should have like asked you guys earlier before the review started, or even emailed Dr. Alexander. But yeah, I don't. I'm supposed to cover that with them. I don't know. It looks a lot like modules even 7 stuff.
Yeah,
me.
it's in module 7.
So yeah, I don't think. I don't know if you guys want to contact Dr. Alexander soon after this or right now. Even one of us can. But yeah, I just feel like that shouldn't. I don't know. You know what I mean? Like it shouldn't be on the test.
Yeah, I don't think it's going to be on the test, guys. Don't worry about that. I think he just made a mistake because we got an email with about, I don't know. We got an email saying that the students didn't have to do number 8 on those study questions, or at least that's what I understood from the email that we got from Dr. Alexander.
But the most important thing for us is just to focus on the the topics that are for sure going to be on the exam, which are stoichiometry, precipitation, atomic structures, moles, things like that. So you guys shouldn't have to worry about things like molarity or anything like that for now. How do you ever do this? Just kidding. So does anyone have any other questions about that problem?
Plus
If not, then we can move on to precipitation reactions real quick. All right, cool. So precipitation reactions, like the word says, it's a reaction that has a precipitate in it, right? So in order to have a precipitate, you guys need to know your solubility rules, which, unless I'm mistaken, you guys have to memorize. I don't know entirely for sure.
They should
just
I
memorize them.
think.
They're not that hard.
Yeah, they're not that bad. I'm just putting a random reaction together real quick. Which makes, oh, I balanced it without even thinking, my bad. So everybody, is the equation balanced or not?
Yes.
Yes, right? Okay, cool. And so is this compound soluble?
Yeah.
Is silver chloride soluble?
No.
No, right? Is silver sulfate soluble?
No.
No, right? And sodium chloride is sodium chloride is sodium chloride soluble?
Yes.
Yes, right?
In class, professor said the sulfates are soluble, right?
Yes, but they have some exceptions. So
Page
for
119.
what he said.
Page 119 of your workbook.
119.
Yes, 119. Sorry, Jeremiah, continue.
No, you're fine. So I didn't put anything with this one because it was just to give you guys practice for being able to tell the difference between a soluble compound and an insoluble compound, because you guys are going to need to be able to go through this quickly. So with that in mind, we can go ahead and do one that has actual numbers in it. When you're doing a precipitate reaction or like a problem, it usually will also be tied in with limiting reagent. So you need to be able to figure out which one's the limiting reagent as well as which one's the precipitate. So let's say we have sodium carbonate, 12 grams of sodium carbonate. Oh, did you guys need to know molarity for precipitate reactions? I don't remember.
Or maybe some
I'd say no.
asking where, I want to say there might be some where they ask like, what's like how much mass of a precipitate is produced, and they give you like 2 masses of reactants.
Okay, that's fine. That's fine. That's all I wanted to know. And then we have sorry, that's barium. Barium chloride. And that goes to make sodium chloride. So, oh, and there's also 27 grams of barium chloride. So, is the equation balanced?
No.
No.
No? Okay. So, what do we need to add and where?
On the product side, a 2 for sodium chloride.
Okay. And anything else?
That'll be it, no?
Yeah. Now, with that in mind, sodium carbonate, is that soluble or insoluble?
Soluble, because
Soluble,
group
right?
1's an exception.
Mm-hmm. All group 1s will always be soluble. Barium chloride, I know it looks really bad, but you know.
That one's soluble.
Nice, nice, nice.
This might be a dumb question, but what makes a compound soluble?
So you guys have a solubility chart. It kind of ties in with like how the difference between like strong and weak electrolytes and things like that. But basically, and if it's soluble, it will be able to break apart into ions, which is why all soluble compounds are electrolytes. And I don't know much about what makes insolubles, but like you could probably look into it, but it's not necessary for Gen Chem 1, so it's up to you. But that was a good question because even I don't know that.
The solubility chart isn't going to be provided on the test, right?
No. To be honest, all I would advise you guys to for sure remember is what's soluble, like how group 1 is always soluble and what's always insoluble, and then like try to remember exceptions. I don't know anything about that, so you can ask my fellow peers for some assistance with remembering these.
I got you. All right. So insolubles, recognize or remember the CCOPS acronym. So CCOPS, that's carbonates, chromates, OH, phosphates, sulfides. Remember, it's IDE ides. Solubles, caching 1A, Kashinga is how I remember it. That's your chlorates, acetates, sulfates. Remember, 8 sulfates, hydroxides. Ignore the I. Hydroxides, nitrates, group 1 elements, and ammonium. There's some exceptions for insolubles. Always, group 1 and ammonia. And then for OH specifically, it's barium hydroxide, because barium hydroxide is just built different. So solubles, the exception here is sulfates. The way I remember is Mr. Cow is happy. So Senor Vaca is happy. So Mr. Cow is happy, or there's something else. And then the group 1, all right, no, sorry, halides. Halides are also happy, right? So H and H, halides are happy. That's how I remember it. There's a lot of other ones like, I think it was like Sir Angel Campos, peanut butter hugger. That's another one I've heard. So Sir Angel Campos, peanut butter hugger. Just remember them. Mr. Cow is happy. Halides are happy. And then here, group 1 and ammonium, also barium hydroxide. Now that's all on page 119. So
yeah, as you guys can see, these are heavy metals. Like these are all lower on the periodic table, so that might be of some use for you guys. These are all group 2. Starts after calcium. But yeah, moving forward, sodium chloride, is that one soluble or insoluble?
Soluble.
Beautiful. And barium carbonate?
Insoluble.
Insoluble. So we're trying to figure out.
Real fast, why is it insoluble if isn't barium an exception to the insoluble rule?
It's only to hydroxides. So with hydroxides, the OH groups, so they'll be soluble when they are bonded to the group 1 element and ammonium, but you also add barium on top of that just for the hydroxides.
Okay, awesome. That makes a lot more sense. Thank you.
Thank you for the clarity, my guy. So obviously we're looking for how much of the precipitate is formed. So with all this in mind, how are we going to figure out how to reach how much precipitate can be formed? What's the first thing we need to do now that we know which ones are aqueous, soluble, or solid, stuff like that? Any ideas where to start?
Nope.
Okay, well, we have givens. We know we have 12 grams of sodium carbonate, and we know we have 27 grams of barium chloride. So, and we also know that in order to go from grams to other types of grams of a different compound, we need to go to a little lovely intermediary or thing that's in the middle. Do you guys happen to know what that is?
Moles.
Beautiful. Yes, moles, right? So how are we going to go from grams to moles to figure out
the total molecular mass, I guess?
Yes. So we have 12 grams of sodium carbonate, right? So how are we going to go from grams of sodium carbonate to moles of sodium carbonate?
Get the molecular weight of sodium carbonate.
Beautiful. So does anyone know what it is?
106.
Beautiful. So we have 106 grams of sodium carbonate. Now, are we going to stop at moles of sodium carbonate, or are we going to keep moving forward, I guess?
What were you asking for?
Are we stopping at moles of sodium carbonate, or are we going until we reach moles of barium carbonate?
Well, are you trying to convert? What are you trying to convert to?
Well, we know we're trying to convert to grams of barium carbonate eventually.
Oh, okay. So your next step would be you're trying to count. You need to cancel out the moles of NaCO with the moles of BaCO.
Okay, which is the molar ratio, right? So
yes, molar ratio.
So how many moles of sodium carbonate do we have in this equation?
1.
1.
1, right? And how many do we have of barium carbonate?
1.
1.
So as you can see, we didn't really need to do this step, but it's good to get in the habit. So we started with grams, so we get rid of those. And then we finally reached moles of barium carbonate, because that will allow us to know which one makes the least amount of moles of barium carbonate. Now, we did it for one of these. Now let's do it for the other one as well, right? So we have 12,
Barium chloride, no?
Yeah, we have 27 grams of barium chloride. What's the molecular weight?
$208.2.
208. Okay. And coincidentally, they also have a 1-to-1 ratio, which leaves us with 1 mole of barium carbonate on top as well. So,
and you always use the same what's it called, compound, like barium carbonate?
Yes.
If you're trying to compare which one makes less.
Because if we don't reach the same amount of moles of if we don't go to the same moles of a product, we have no way of telling which one makes the least amount of moles of said product. Yeah.
Thank you.
So why do we do the 1-to-1?
So the only reason why we did it this time, it was just a habit, because I normally do it, but like for future reference, you don't have to if it's a 1-to-1. But the reason why so the reason why we do it is because, like, let's say we had a 2 in front of here, we don't, but let's say we did have a 2 in front, then we would put a 2 down here. And so that would mean that we need to divide this by 2. And the reason why I take the extra step and do that molar ratio like that is because people often mistake whether or not to divide or multiply the molar ratio. And so it's like a simple problem that you can easily fix just by doing this. Does that make sense for everyone?
Yeah. Yeah, I like always adding it.
Yeah.
Another thing I like to add, it's important to keep track of your units, even though you're staying within moles. Also keep track of which compound you're working on, because you might say you'd be working on one compound, but then you wouldn't even notice if you converted to the other, or if you haven't. It's important. It's always important to keep track of those.
Oh yeah, that's why I put the compounds names next to the units as well. It makes it easier to keep track of. Yeah. So with all this in mind, does anyone know the amount of moles we get of barium carbonate from sodium carbonate?
0.113.
0.113 moles. Okay. And then from barium chloride?
0.129.
0.129. So which one produces the least amount of barium carbonate? 0.113 or 0.129? Sodium carbonate. So this is our limiting reagent. Oh, the reason why I'm asking is because it will probably ask for the limiting reagent. So it's just good to get in the habit now. Now, we know that the 0.113 is the most amount of moles we can make of barium carbonate. So what's the next step we need to do to figure out how much precipitate is formed? Any ideas?
Not sure, but we divide.
No clue.
Wait, sorry, did you say 0.113 was the most that we can make?
Yes. So since that's the lower number, that means that's the most we can make, because that the most we can make is whatever's the least. Exactly. Boom. Beautiful. So
are we converting moles back to grams again?
yes, because we're trying to figure out the amount of grams we can make. So how do we do that?
One more at the bottom of barium.
And how many grams do we have?
But why are we converting it to grams again?
It's because we're trying to see how much precipitate is formed. So when you're asking for how much of something's made, it's usually in grams, not moles, unless it specifically states otherwise.
Okay.
I'd also like to add, pay attention to your units, because even though we're just asking to convert it, be careful. It might say like kilograms or even megagrams. So kind of pay attention to what specifically it's asking for.
On this one, do we put that to like the molecular mass or just the grams that they were given?
The molecular mass. We don't have a given grams of barium carbonate, so we're trying to figure out how much can be made. For you people, I'm sorry.
Do we need to find molecular weight for this?
Yes, you would need the molecular weight in this case.
197.28. Is that right?
7.28.
Oh, 197.
Oh, 197. Okay, that makes more sense. That's a 9. A really thick 9. Okay. Barium carbonate. So moles are gone. Grams of barium carbonate. Is that what we were looking for?
Yes.
Okay, then without further ado, you multiply these bad boys, get your nice little answer. And what do you guys get?
22.29.
Wait, what?
22.29 or 22.3.
22.3 grams of barium carbonate.
On this one, would it be 22.3?
Mm-hmm.
Yeah.
Like, I mean, like counting like the decimal points in the.
So,
yes.
Significant figures.
So, I don't know about anyone else, but like, unless like it's for something that's experimental, or unless like you're given a certain amount of significant figures that you can use, I don't really see a point in looking for something like that. Like for me, the furthest I go is to the 10th place, which would be 0.30. But you, since it's multiple choice, you guys won't need to worry about that, because Dr. Alexander's not an evil person, so you guys should be fine.
Yeah, just remember it's multiple choice. So if like, you don't really need to put in significant figures if you're choosing A, B, C, D,
Mm-hmm.
So the answer was the limiting reagent and the 22.3 grams.
Yes. So sometimes they're like I guess compounded questions. Like it'll ask like, I don't know, question 7, what's the limiting reagent from that comes from sodium carbonate and chloride, which we figured out as sodium carbonate. And then question 8 will be like, refer to question 7, what's the most amount of precipitate that can be made from sodium carbonate and barium chloride with this given information, the 27 grams and the 12. So it's just good practice, because if you don't figure out which one is smaller, then you can't get this lovely number down here. So everyone good? Everyone understand?
Yeah. So just to be sure, we basically utilize the limiting reagent to multiply by I guess one of the products we're given, right, to find how much we can make of that certain compound.
Yes, perfect.
Okay.
And just so you guys know, this would be your theoretical yield. So this is the most amount that you can possibly make. And then if you like for a lab, you would have an experimental yield, or if they give you a certain amount that was made, you would divide the experimental by how much you could possibly have. Is anyone confused, or like, do I need to explain further?
Yeah, you confused me.
Okay, so like, let's say that they said that they did this experiment and they made 13 grams of barium carbonate. This is the most that you can make down here, but this is how much they made. So you would get, in order to find the percent yield, you would divide the, I did something. To find the percent yield, you would divide the amount that they got, this 13, by the amount that could possibly be made, which is the 22.3. And that will give you percent yield. I don't know if you need to know that though.
So adding on to that, just so to better understand what Jeremiah is saying, on your homework for module 4, I think everybody's has been assigned it already. Everybody should have in your respective workshops. Number 5 is kind of a problem as to very similar as to what Jeremiah is saying, like the example. So you can look at that one if you don't understand what he meant. But yeah, number 5 is a problem similar to what he's saying. So if you a certain amount of grams of something and you do it on your own and you get a different amount, so you do the percent yield equation, which is just your actual over your theoretical. So everybody has their workbooks. You can look at number 5 if you want, and just if you've already done it and you got the right answer, that's basically what he's saying.
All right, everyone good? Everyone understand? Everyone feel smarter?
Yeah. Can you go over question number 8 for study set 6?
Question number 8 from study 6. Let's see. It's 4, 6. So, wait. Click. Wait. 6.
Oh, I also found the question on the one we were doing before, I think it was number 7 or something.
Oh,
that is also explained in your lecture one. So just look at the lecture PowerPoint. I know you guys have that. It's 3.2.5, I believe. So yeah, that's if you want the explanation.
Yeah, what he said. What was the question for study 6?
Question 8.
Question 8? Question 8. Okay, predict whether or not a precipitation reaction will occur if the pairs of solutions are grouped below. All right. Excuse me. So, does anyone else hear like a noise in the background?
Yeah, I hear like a chime.
Okay, good, because I thought I was going crazy. That. But yeah, so number 8. So you guys, you have your solubility tables. You should be able to figure this one out. So for the first one, let's just make it simpler. Sodium. What under the soluble, since we know it's soluble because it's aqueous, what category does it fall under? What's sodium? Or what's sodium on the periodic table?
It's group 1.
It's group
So
1, right?
So it's soluble.
Yeah. And potassium?
Same.
It's also group 1, right? So since they're both group 1, what does that let you know? Will there be a precipitate or not?
Yeah.
I don't think so.
Oh, right?
No.
Because they're both group 1. I don't know if someone said that. I wasn't trying to like throw you for
I
a
wasn't
loop.
sure, so I was like, I don't think so.
But yeah, since they're both group 1, that means that they won't have a precipitate, which means there won't be a reaction.
So if there's a compound whose both elements, or actually both, or what would say, like compounds, I guess, too, are soluble, then it won't create a precipitate. Like, it won't be a reaction.
Well, only if both of them are group 1, then you can automatically assume that, because group 1s are always soluble. Looking at the next one, potassium. Well, we already know, I guess.
I got
I'm sorry?
confused. So if both of them are soluble, they won't have a reaction, or
No. So, okay, your guys' insolubility chart, or for their solubility chart, and a compound is soluble if it's a group 1, and for insoluble, for all of them, they have an exception for group 1 elements. So if you guys remember this, that means that if both are group 1 elements, then they'll always be soluble.
Also ammonia, so group 1 and ammonia, which is like NH4 plus.
Oh, okay, that makes sense. So that means they will create a solid, right?
No, that means that they won't create a solid.
Yeah, so they won't. All right, that makes sense.
Cool. Now, looking at the second one, so that's the first one. The second one. Potassium, it's a group 1, right?
Yes.
So with that in mind, that means that it's automatically going to be aqueous. I don't know if I'm cheating by telling you guys this, but I might. And then the next part. Okay, we have a calcium, right? Is that one always soluble? Is it under soluble?
It's an insoluble exception.
Perfect, right? Oh, wait.
Wait,
It's
only when it's combined with a sulfate, though.
Okay, and so what about carbonate? Is that one insoluble or soluble?
Insoluble.
Okay. Is calcium an exception for it to be soluble or no?
No.
No, right? Okay.
No.
So calcium carbonate. So is it a solid or aqueous?
Solid.
It'll produce a precipitate, right?
Beautiful. So I guess that's all it's asking for. Okay, on to number 3.
So how do you know it will create a precipitate?
So a precipitate's a solid, right? And the solid is insoluble. So like all 3 of those words can just combine to be whatever you want, like just choose one of the 3. And as long as you remember which ones are insoluble, you'll know if you make a precipitate or not. Does that answer your question?
Kind of.
Okay.
A precipitate is an insoluble thing in a reaction. So if it's an insoluble, then it's a precipitate. It's just a fancy word that we use.
Having exceptions too with the soluble ones?
Yes.
If it's, well, basically, if it's insoluble, it's a precipitate. If it's soluble, it's aqueous. That's all you need to know.
Just be sure to always look at like what's the soluble substance, which is usually like your second part of the compound. So just look at it whether it's soluble or insoluble, and then you look at what it's bonded to. So like if we look at the potassium nitrate that's been produced, we see that nitrate, okay, it is soluble. And if we look at the exceptions, there's no exceptions for nitrates, so we can assume that no matter what it's bonded to, it'll always be soluble. So we look at the calcium carbonate. The carbonates are insoluble to whatever they're bonded to, but let's make sure it's not bonded to an exception. Since calcium is not an exception to carbonate, we can for sure say that it is a precipitate. So it'll be a solid. Does that kind of make sense?
Yeah, that was a good explanation.
Nice, good job, Alan. Well, that wasn't supposed to sound what's called, but yeah. So moving on to number 3. So sodium. It's a group 1, right?
Yes.
Yes, right? So sodium chloride. Soluble or insoluble?
Soluble.
All right. And then calcium nitrate. Soluble or insoluble?
Well, calcium is soluble, right? Since it's in group 1.
Calcium's group 2, but we know about nitrates.
Oh, I was thinking potassium. Sorry.
No, you're good. You're good. So what do we know about nitrate?
Right?
Yeah, right. I mean, just so you guys know, we also just had calcium nitrate up here. So these are both aqueous, right?
So calcium nitrate is. Is that what you're saying? No, it's not. It's insoluble.
So remember, we look at the second part of the compound, right? So we see nitrate. We see if it's soluble or insoluble. We see that it is soluble. We check if it has any exceptions, and nitrate has no exceptions. So we can assume that no matter what it's bonded to, all nitrates are soluble.
Okay.
Yeah. You're basically seeing whatever's on the left side, the metal being with whatever's on the right side of the other side, or like the other compound. So like, well, we know that both of these are soluble now. So no reaction. Number 4. So like silver, we're trying to imagine silver with chloride. And we're trying to see calcium with nitrate and see if either of those will make a solid.
For number 3, they're since both are soluble, then it won't create a precipitate.
No, and since it won't create a precipitate, that means that no reaction will occur.
All right, thanks.
So yeah, so silver chloride, right? Soluble or insoluble? Remember what chloride is as well?
Insoluble.
Soluble.
Yeah, calcium is normally soluble, right?
Yeah.
Do halides have any exceptions since chloride's an exception?
Silver has one.
I mean, a halide.
Silver has one.
Silver's an exception.
So it's a solid.
It's insoluble, right? I'm just like Jonathan. I'm trying to like lead you to the
Yeah, it is.
Giving you the answer. All right, and calcium nitrate, is it soluble or insoluble?
Soluble.
Soluble, right? So calcium nitrate. Let me just write number 4 a little bigger. So calcium chloride plus silver nitrate. Aqueous. Goes to make, oh, I made it too big. Chloride and calcium nitrate. So the second part of the question asks for it to be balanced. So is this one balanced?
Yeah.
It's balanced?
No, we have 2.
2 what?
Nitrates.
2 nitrates, right? Okay, so in order to balance it, what do we need to do?
We put a 2 in the
In front of what?
silver nitrate.
Okay.
I mean, you have 2 silvers.
Yeah.
Oh, and the 2 right here?
Yeah.
All right, is it balanced? Are we good?
Wait, a 2 where? In front of the silver nitrate and where else?
And I'm guessing there's another 2 in front of calcium chloride. I'm getting lost.
Wait. Let me just erase this real quick. Wait, so okay, so we have 2 silvers right here, right? Yes. We got 2 nitrates. So the nitrates are balanced. Are the silvers balanced?
No.
Okay, how would we do that?
Put a 2 in front of the silvers. Silver chloride.
Okay, so we have 2 in front of the silver chloride.
And we have 2 chloride though.
So is it balanced now?
No. Oh yeah, actually yes. We have 2 silver chlorides and calcium chloride.
Just so you guys know, this is a 2. I don't know how bad my
didn't see
handwriting is, yet, but like that's a 2. That's aqueous. That's a 2. That's a 3. That's aqueous. This is a G. It's a really bad one, but it's a G nonetheless. That's a 3. That's a 2 aqueous, and that's solid. So, putting my bad handwriting to the side, is it balanced?
Yes.
All right. Any other questions pertaining to precipitates and balancing and stoichiometry?
So I just have a question. So for the third question, the third part, why did it have a reaction?
So since we found out that, or figured out that sodium chloride would be aqueous and the calcium nitrate would also be aqueous, since everything's aqueous, it won't form a precipitate. And since it can't form a precipitate, no reaction will occur. The reason for this is since no precipitate is forming, all of these ions are just floating in this water. They're not able to bond with something and get out of the water. So they just stay as ions or bond with each other. But like, yeah, nothing will really happen. They're all just floating in there like a soup.
Okay, thank you.
I have another question. So you know how on the fourth question, on the fourth example, you put silver chloride and then calcium nitrate. How did you know to put calcium nitrate and not nitrate calcium? You get what I mean?
So calcium is a metal, and way back in module 2, what we were taught is to put the cation or the metal first, and then the anion and the negative second.
Okay, that makes sense. Cations first.
Yeah.
For silver chloride, we know chloride are soluble, right? So how's that solid?
Where?
Not all chlorides are, or
So
not all
it's chloride.
chlorides are soluble.
So yeah, so chlorine or chloride falls under this lovely column next to noble gases called halogens, or when they're in an ionic form, they're called halides, right?
Oh, that.
Yeah, and those halides have a few exceptions, which this lucky boy right here just happened to be. Well, I don't know if he's lucky.
The ones that are next to the noble gases?
Yes, to the left of noble gases. So fluorine, chlorine. Yeah, fluoride, chloride. Yeah.
Got it. All right. Thanks.
All right. So, any more questions about this?
When you're dealing with silver, do you just automatically assume it's just a plus and
Yes.
like no other
silver will
charge?
always be a +1 charge.
Okay.
Yeah, even though silver is like a transition metal, yeah, well, it can't have any other charges other than +1, really.
That's weird.
So it's like one of those few exceptions.
So, any other questions pertaining to this real quick? We all good?
Here, Jeremiah, there's no any other questions to this. Someone here, Jacqueline, had a question about like if we can look at set 4, question 12, like the iron Fe kind of confuser there. So can we look at that?
Okay. So, we're gonna look at that one, and then after that, we're gonna talk about atomic structures for a little bit. That way, everyone is copacetic as to what it is that we're doing.
Yeah, atomic structures is that's what it deals with. So.
Oh, does it really?
Yeah.
Oh well, look at this. Wait, let me see which one.
It's on the same wavelength.
I know it's because they're built different. So, oh, what question was it again?
12.
12. All right, all right. So, how many electrons are located in each of the electron shells for the following atoms? So, in order for us to do this, we first need to know what an electron shell is. Does anyone not know what an electron shell is? Just like click this button. All right, so everyone knows what an electron shell is, right? So pretty much like every period is an electron shell. Carbon on the second period, because hydrogen and helium are the first. So special. And then we can just move on to the second one, which is where carbon is, like right here.
Wait, Jeremiah, do you want me to share a periodic table? I think it's easier to visualize that way.
That's fine. That's fine.
Cool. There you go.
All right. So looking for the word. Found the word. Oh, wait. Give me a second. I see my face.
Okay, well, I'll explain this one. I'll explain this one then.
Go for it.
As Jeremiah said, each periodic each period is an electron shell. So, for example, how much what electron shell is potassium in, or how many electron shells does it have?
4.
Perfect, right? Because it's on the 4th period. So it's a interesting thing, and we really get into this later on around like module, I forgot what it was, electron configuration. So some things that you do need to remember is that the first shell only has these two, right? Because you move the helium over here, right? First shell only has 2, can only have 2, right? Second shell, it can have 8, right? Because all of these, there's 8 periods in the periodic table. But the third shell is really tricky, right? Because the third shell is part of, really in reality, this is the third shell, but we don't get to use that shell until we have to go up, a different level, right? So for the third, you really just count these ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all that stuff. But when you get to this 4th element, and I think this is where your trouble is, or where your question is, right here, your 4th, remember you fill up these 4th ones and then all of these 3D ones, and then you go into the 4, 6 shell. So you always fill up the first 2 in the 4 shell, and then you fill up the 10 in the 3D shell. It's kind of confusing, but just remember for every section, this one moves up a shell, right? So all of these will use that 3D shell. Just really in reality, what you're going to be looking at and what Dr. Alexander probably wants you to know is that you fill up the first shell, which only has 2. Then you fill up the second shell, which has all 8 of these. You fill up the third shell, which you fill up 8 of them before you can fill up this part. Does that make sense? So I don't know if you're looking at like where he had gallium. In the first shell, he only has 2. In the second shell, he has 8. In the third shell, he has 18 because of all this, plus this. And then in the 4th shell, he has 3. And that's where he's getting those numbers from. And then if you can see, it all adds up to 31.
So for shell 3, you skip to the 4th column, right?
Yeah, so before you finish using all 18 I guess spaces in shell 3, you have to skip to the first 2 of the 4th shell. So yeah, exactly correct.
Okay.
And then or another notation you can look at is 1s2 so 1s2, 2s2, 2p6, and remember 3s2, 3p6, 4s2, and then 3d10, right? And then this is something we'll learn later on in the course. This is called electron configuration. But as you can see, this always follows a pattern of first shell, second shell, and then you add these ones, it's 8. Third shell, you add these 8 before going on to the 4th shell, and then we start adding stuff in the D shell. So if it has more than, okay, does that make sense? I don't want to go further than I need to. So just recognize this pattern.
A simplified version would be the first shell has 2 electrons, second shell has 8, third has 18.
Yes.
And then the 4th has 8.
4th has Ooh, okay, for what you need to know on the exam, yeah, fourth shell has 8.
Okay.
Yeah, I don't think you're
then
gonna be covering all of this. Yeah.
The fourth shell doesn't have 32.
It does, but you're not gonna see that because the 32 comes from this part. And if you can see, there's kind of 4 sections on the block. There's this first section, this second section, this middle section, and this bottom section. And so when we're talking about the 4, this is again, you don't need to really remember this. I'm stressing you, don't need to remember this right now. But these are the 4 sections, and this is the 4 shells, if you will, right? And then once you start seeing these shells, this one moves up, and then this one moves up twice. That's where the 32 comes from. But again, you don't need to remember this.
Okay.
Okay. So for that, that's what he means by shells, right? Any questions on that? Or do you want me to go over it again a little bit different?
Yeah, can you show like an example? I guess like
yeah,
like
perfect.
Solubility
Okay, I'll do what Ivan said. Fe. So look at Fe. Where is Fe on the table?
Number 26.
Number 26. So Fe has 2 in the first shell. Fe has all 6 in the second shell.
8, no?
Or sorry, all 8. Yeah, my bad. And then for the third shell, it has all 8 again. And for the fourth shell, it has 2. And then it's 1, 2, 3, 4, 5, 6. But remember, this transition metals are part of this shell. So that's 8 plus 6, which you get 14.
The third shell has 8 or 18? In the sense of the exam, for now.
In the sense of the exam, the third shell has 18, right? This will be 9. This will be 10, 11, 12, 13, 14, 15, 16, 17, 18. That's what I mean by the third shell has 18. And this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, or 7, 8. Did I lose you guys there?
Why did you start from 11? Why did you start from 11?
Oh, that's 9. I'm sorry.
Oh,
That's a 9.
okay. Oh, okay.
Yeah, because that's 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
So iron on the third shell has 8 or 18?
It has 18. Or
Okay.
no, sorry. It has 14, right? Because that's where it ends up.
Oh, perfect. Okay, I get you now.
I know this one's not in the workbook for what you guys have read so far. So definitely this is the time to ask questions because I know 100% that your peers probably haven't covered this before. So if you're confused, speak up right now.
How many does it have in the fourth shell if you have to go back and add the 6 to the third shell?
In the fourth shell, technically, you would only have technically only 2, because if you notice that here, let me Jonathan, if you don't mind.
Yeah, go ahead.
Here, let me switch to red. So if you notice, this sort of row here was kind of been labeled as like 3D. Since this is like labeled as the third shell, it would kind of be part of this group up here, but you wouldn't count it until once you get to the fourth. And since this fourth shell is at a higher level than this one right here, you would count the electrons within this shell. And say if you were to go any farther than this, including the ones here, like say for example, selenium, you would like selenium here, you would count all the electrons from this, just counting from here. And these 2 here would be like 1, 2, 3, 4, 5, 6, and its outermost shell.
Alan, are you trying to explain to them why the 3D goes with the third shell?
Yeah, like the third shell. Like because she asked like how many would be in the fourth shell, and technically it's like the outermost shell because this 3D is beneath this 4S.
Okay. Just so you guys know, because it like for lack of confusion, because if you guys like the reason for why it's 3D is like really confusing. But as long as you guys know that once it reaches the fourth shell, like the 4Ps, that's when you implement 3D. That's all you need to know. Once it passes P for the fourth shell and up, that's when you'll implement the D shell.
So to kind of simplify answering your question, since this 3D is beneath this 4S, like in the case of iron here, it would technically only have 2 electrons in its fourth shell.
You know, I think another thing we should do right now is I think we can just do another example. And if you guys see the example, maybe it'll start to click. So what's another element in that? Or give me another element.
Do silver.
All right, silver. Too far. Keep it above this area.
So Dr. Alexander will most likely keep everything in the fourth shell, correct?
After the fourth period, I highly doubt you're gonna see it.
Okay.
All right. CU.
How about bromine? Oh.
All right, let's do copper first, and then we can do bromine. So remember that, again, these are your 1, 2, 3, 4. And just for this purpose, you can shift, or you can just count how many elements are here. Right, so in the first shell, how many would there be?
2.
2, right? In the second shell, how many would there be?
8.
8, right? And then in the third shell, for now, how many would there be?
8.
8, perfect. And then in the fourth shell, remember that the fourth shell ends here and begins again here, right? So are we going even past 3 and above?
No.
No, right? So the fourth shell is just going to remain at 2. And then from here, we can just start counting and adding on to this third shell, because all of this is part of the third shell. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 plus 8 is 17, right? And so your final answer would be 2, 8, 17, and then 2.
Okay, that makes much more sense.
Right?
Cool.
And again, it's another practice. So let's do bromine together. And then you're gonna start seeing patterns. So let's do bromine. How many in the first shell of bromine?
2.
2, right? Because it's always 2. And then how many in the second shell?
8.
8, perfect. How many in the third shell for now?
8.
8, right? And then how many in the fourth shell? Well, that's 1, 2. Skip, and then 3, 4, 5, 6, 7. So there's 7. But remember, we skipped all of these ones, and that's 10 of those. So we have to add 10 to the 3 block. Right? And you basically move this one up. So that's how it's going to be, right? That's oops, that's 10. So your final answer would be 17, or 2, 8, 18, 17. Does that make sense? Or 7, 7, 7, 7, 7, 7. Does that make sense now?
Yes.
A lot more sense, yeah.
So just to rephrase, just to make sure that I'm getting this, for the first one, the most you get is 2 electrons, right? For the second one will be 8, or the third one will be 18, right?
Correct.
Okay. And then the fourth one, I guess I don't need to worry about it too much, even though in case we get something, it will be like less than 8, hopefully, during the exam. Right?
Yeah. I can also teach you on how to do these. So these ones, just kidding. I cannot. I'm gonna confuse you guys. Yeah. Hopefully you don't get anything past this shell.
I think that knowledge should be enough, right? At least for this exam.
At least for this exam, you should be able to solve everything.
Get it. Thanks.
So it can be 2, 8, then it can be 8 or 18, and this one is 8 technically. Between 8
So if you
and 8
see-
for the third level.
Yeah. So if you see something that has that is in this third period, you know for sure this is going to be 8 or less, right? But if you see something in this fourth period, then that means it's going to be 9 or more. Does that make sense?
Yeah.
And then this talks about this third level. All right, ask questions now because I know you haven't seen this in workshop. I will take your silence as we can move on. All right, what else questions do you have? Okay, let's talk about valence electrons, right? We'll try to tie this in, right? We'll talk about valence electrons. So what is a maximum number of valence electrons?
8.
8, right? So 8 is a maximum number of valence electrons. And you know, that's 1, 2, 3, 4, 5. You guys know how to get the maximum of that. But if you can see about how we were doing, how this is a 1s2, 2s2, 2p2, 3s2, 3p6. You notice when I was talking about that, we start in the fourth one and we skip all of this, and this goes down to a lower energy level, as Jeremiah said. And then we have these ones. These are where the electrons or the valence electrons come from. Remember, the outermost, as I said, in krypton, say like 4 would equal 8, right? And you're not going to see 4, the fourth shall rise higher until you go lower into the periodic table. But this is where that number comes from. And I think that's what Dr. Alexander was trying to say when he was telling you about this thing. Just notice that your 8 comes from 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to stop talking now. You guys have questions? Did I lose you? Do I need to repeat anything? Do I need to move on?
Like what we just recovered, what we covered before, no?
Okay, let's move on. So what are the topics that is going to be covered in the exam? Do you guys know? Have we told you?
Yeah, it's 4, 5, and 6. Modules 4, 5, 6.
4, 5, 6.
But atomic structures, stoichiometry, solutions, and precipitation reactions.
Yes, the stoichiometry, solutions, and precipitation reactions. So we've already covered precipitation reactions. That's all your solubility rules. You know, basically knowing if it's solid in the solution, then it's a precipitate. And stoichiometry, you guys know how to do that. That's dimensional analysis. But some tips on dimensional analysis, because I know some students struggle with this. Always, 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 number one thing you need to do, write down what you know. That's some of this may include where you're starting from and then where you're ending. And then always, always, always do your units. I know it seems cluttered, it's going to get messy, but always, always, always put your units, because once you find out, hey, I'm at the end, then you know where to stop. And I know a lot of students don't know or confused, oh, when should I stop? When should I keep going? That's why you have to write these things down before you start this. before you start the problem. And then once your units match, then you're done. So what do you guys want to review? Question 5 of the 5th set. All right. Can you unmute yourself and just tell me what it is so I don't have to go looking for it?
It's saying a compound of titanium and oxygen has a composition by mass of 60% titanium and 40% oxygen. Determine the empirical formula of the compound, and that's it.
All right, easy. So titanium, oxygen, we know it's gonna be something like, oh wait, do you guys wanna, I feel like I've talked to you guys. Do you guys, Alan, Claudia, Andre, do you guys wanna take over?
However, fine. Here, if you want, I can just step in if you feel like you're tired.
No, I don't mind. You go ahead, Alan.
Hey, yeah, here. So what we can assume here, since this equals 100%, we can assume that our sample is equal to, let me switch to blue, is equal to like 100%. So 100%, we can assume that our sample is equal to 100 grams. So what we can do here is directly convert our percentages to grams. So our 60% of titanium and our 40% of oxygen can go to 60 grams of titanium as well as 40 grams of oxygen. Now from here, let's see, from here we would get the, we would convert these into our moles. So we would take the molar mass of titanium and the molar mass of oxygen. So here, let me just move this. Let's see, let's just drag this out down here. What we use are a molar mass composition. Now, can anyone tell me what the molar mass would be for each of these, starting with titanium?
Titanium is 47.87.
So 40, so it'll be 47.87.
Yeah.
Grams for every 1 mole. And who can tell me the one for oxygen?
That's 16.
So 16 grams of oxygen over 1 mole of oxygen. So here we can just cancel out each of our desired units that we can cross. Now, who can tell me what's the number of moles in 60 grams of oxygen, titanium? I mean,
it's 1.25 moles.
1.25 moles of titanium. And then for oxygen, who can tell me the one for oxygen? 0.5. I believe so. I feel if I did I hear someone say 2.5?
Yeah, it's 2.5.
Okay, perfect. So now that we have our number of moles, what we do here is you would divide each of these numbers by the smallest number of moles. So since we see that 1.25 is smaller than 2.5, divide them.
This one, would we consider the limit reagent and all that? Or
technically, there's no reaction taking place, so we wouldn't know of a reaction taking place. So there's no limiting reagent because this is all one compound. So we're just trying to find the empirical formula. Am I right? Yeah.
Right.
So we're just trying to find like what subscripts would go under like each of these elements when they're in a compound. And this is how we do it. So from going from our percentages, assuming that it is 100% equaling 100 grams, we will assume there will be the number of grams equivalent to their percentages, convert our grams to moles. And then here we would divide the smallest moles into each of these numbers. So be 1.25 divided by 1.25, and then 2.5 divided by 1.25. And then from there, since we can obviously assume that this is 1, and then from 2.5 divided by 1.25. And then these numbers, these would be your subscripts for your empirical formula. So if we, let me fix that. So let's see here. Let me erase some of this here. So I just gotta move the camera around. There we go. So let me erase this here since we know that we have to convert to molar mass. And now, so here we have our titanium and our oxygen. we look at the numbers that we got from it, we see that from moles of oxygen, of titanium, we dividing by the molar, yes, Emily, that would be correct. After we divide by the smallest number of moles, titanium would just be 1 and oxygen would have a subscript of 2. Since we know that for us having the subscript of 1, we don't really need to include the 1 since it already, just the element being there denotes that it's already there. So you would have TiO2. And then this would be your empirical formula. Remember, this isn't your molecular, this is your empirical. Does that help answer any questions?
All right, Alan, I'm
Are there
going to
any-
clear your drawing.
Yeah,
Is that
let's
fine?
do that.
All right.
Yeah, that's fine.
Cool.
So does
So
anyone
when you're
have
doing
any-
this, oh, sorry, I'm just gonna butt
No,
in
yeah,
here. When you're doing this, the steps is percent to grams, grams to moles, divide by small, and this last part is optional. Multiply till whole. Right, because let's say, C and O, right? If you have 1, 1.5, and 2, you're gonna have to multiply. This is just if you need to, so this is optional if you need to. You can't have 1.5 or 0.5 of an atom of nitrogen, it just doesn't make sense. So we want whole number coefficients right here. That means just multiply that by 2. So it's gonna look something like 2, 3, 4. So percent to grams, grams to moles, divide by small, multiply to whole. Yeah, that's all I gotta say.
So how do you know you need to multiply?
So when you divide by small, or this part, after you divide by the smallest one, and you get something right here, where it's 1.52, if you still have a decimal, or if you still have a decimal in there, you need to multiply it until it's not a decimal. Does that make sense?
So if we have like 1.8, do I need to multiply?
Yes.
Okay. Thanks.
But remember, divide by small before you have to multiply.
Yes. Okay.
You got this.
What if you have 2 decimals?
If you have 2 decimals, say like 2.251 and 3.5, all of them have to be, you're just trial and error, man. All of them have to be whole numbers. Most likely you'll have to multiply that by 4. You're gonna look something like 9, 4, and whatever that is. 14? Don't quote me on that though. So yeah, just all of them have to be whole numbers. So just plug and chug, try to see, try to see if it makes sense. If it doesn't, if not, just keep going, man.
And
I think Claudia has something to say.
Yeah, she
Oh
does.
yeah, I have something to say about the how do you know in trial and error. The way I do it, can I write on this? How do I write on it? Okay, there, annotate. Okay, cool, I got it. Thank you. So the way I do it is if it ends in 0.25, in order to get the nearest whole number, like 1, because that's what you want, what do you think you're gonna multiply this by? Someone just put it in chat.
By 2. Oh no, 4.
By 4, yeah, because then you're gonna go to the nearest whole number, which is, I just put 1 just so you can know this is your nearest whole number, right? So let's just say we have something like 0.5. And again, you want your nearest whole number, so I'm just gonna say 1. So what are you gonna multiply it by to get 1?
2.
Yeah. And let's just give you a harder number, which is 0.33. And this is gonna give you 0.99. But it's still gonna give you to the nearest whole number, and that's exactly what we want. So what number are you gonna multiply by?
3.
3. Yeah. If that helps, I hope it does. But that's just simply putting it. If it helps. Okay, that's it. That's all I have to say. Let me erase it. You're welcome. There's another hard problem that I think you had in your module though. It was like you got numbers like 0.66 or like 1.66 and then 1.33 and then like 1. So these are technically the same. You would have to multiply by 3 again to get to the nearest whole number, and this one of course as well. Yeah, just remember, because this is again 0.33 to the nearest whole number, and this is 0.33 to the nearest whole number as well, which would be 1 and this would be 2, and that's way too far. So if it's 0.15, if it's less than or equal to 0.15, you could round, but if it's not, you're gonna have to do this thing that I'm doing here. Can you go over question 5, set 6, please? Which one's that one? If someone can tell me what that one is.
Again, if you do have a question, it is much easier for all of us if you just unmute your mic.
It's the atmosphere is 78% of nitrogen by volume.
Oh, the atmosphere. Okay, thank you.
How many milliliters of nitrogen is contained in 50 milliliters of air?
These are so weird. Okay. So we want to find milliliters of nitrogen gas. 50 milliliters of air. Jonathan, do you know this one? Because it looks like you do.
He went over it in the or I don't know if he went over it in lecture, I think, didn't he? I think it's the atmosphere. Yeah, the air that we breathe technically is nitrogen. The atmosphere is just it's trying to throw you off, honestly. It doesn't really have to do with the problem. It's just there to throw you off. It's very much simpler than it seems. So if you have 50 milliliters of air, which is the air you breathe in the atmosphere and all that, and 78% of it is composed of nitrogen, and it's composed of other gases. Technically, like the air you breathe, it's composed of many gases, oxygen, nitrogen, and some other ones. But nitrogen composes of 78% of it. So if you have 50 milliliters of air, what do you think you needed? I don't know if it's kind of much more simpler than I feel like you guys think it is. So what do you think we'd have to do? Yeah, Claudia's kind of writing it out right now, I think. So yeah, 78% out of 100, yeah. So if you have 50 and 78% of that is nitrogen, what do you think you need to do in the problem to figure out the percentage? Yeah, it's just 50, yeah, the 50 times the 0.78. Which should give you the 39, the answer that Dr. Alexander posted. So yeah, and you can even you can even check it. Let me 39. Yeah, you can even check it. You can do 39 out of 50. So this is your answer, right? I can't even write it. Hold on, let me annotate it. So you can even check it just by doing this. You have 39 milliliters out of 50, and that should give you about 0.78. So remember, just to turn it into a percentage, you multiply times 100, so it's 78%. So yeah, that's just to check your answer. This is just to check your answer, but this is usually the process, and it's pretty straightforward, pretty simple. But yeah, the atmosphere, I feel like everybody got thrown off maybe by looking at the milliliters and the atmosphere. Honestly, it's just there to, yeah, it's just the only purpose of that, I feel like, is to throw you guys off, to make you feel like you guys need to do more steps than you should. But yeah, just remember to always read your problems very carefully. And yeah, if you look at this and you've known that in lecture you haven't really gone over atmosphere and you really haven't gone over using milliliters and all that, just remember to think about that. Like if you haven't used it, it probably doesn't really factor that much into the problem at the moment. Does that make sense to everybody? All right, hopefully it does, and hopefully my explanation made sense. But yeah.
I want to stress something Andre said. A lot of the times chemistry is just that simple. It's just as simple as 50 times 0.78. So that's why just try not to overthink it. You know, it can get complicated at times, but just keep a level head and just recognize what your problem is asking you and what you think would be the best way to approach it. Right. So yeah, sometimes it's just as simple as this. You know, don't get scared by it.
Yeah, and kind of to add on to that, like going forward through the semester, you will be given like some like values or units that like will be useless for you to solve. They're just there to kind of like throw you off thinking you need them. So just remember that, like going off of what Jonathan said, look at what you need and then look back at what you have and then see what you can do with like just the minimum of what you need.
Yeah. And just remember you guys are smarter than you think, so don't doubt yourselves too much also on that. All right. But what else are we covering now? What else do you want to go over? Is this recording?
I think the recording is gonna be posted on the YouTube channel, right? The Empirical YouTube channel.
Yes, sir.
All right. Jonathan, you said you were recording it?
I thought you were recording it, man. No, I'm kidding. I'm recording it.
Don't scare me and the 50 people left in here.
No, I'm kidding. Yeah, no, I'm recording it. So.
All right.
Do you guys want me to go over the problem, the first one? Because we figured it out, me and Jeremiah. The first one we went over, guys. Like the very first one with like the CO, whatever.
I didn't do anything. I just read.
Hey, that's not true. Yes, okay, we're gonna go over that then. And with H2O, right? Okay, so you did figure this out though, Jeremiah, but what Jeremiah said that actually I forgot to do, I just did the rest, is the way he found, I think in the PowerPoint, it said that the amount of carbon in carbon dioxide is 27 point, what was it, 3%? And then the amount of oxygen in H2O was 11.1%. And if you saw the PowerPoint, it should be like this. But the way we got this,
I think it was hydrogen, not oxygen.
oh frick, sorry, hydrogen was 11. There you go, was 11.1, right? Okay, but the way I'm gonna explain how we got this because I don't want you guys to get confused. So remember that's how many moles of C do we have? Anyone? One. Okay. And how much does it weigh? How much does carbon weigh?
12 grams.
Yeah, 12.01 grams. Good. Okay. And how much? Okay. And then I'm just going to say this is a percent composition, by the way. How much does the whole molecule weigh? Carbon dioxide. I don't even know if I have it here, but.
Is it 44?
Yeah, 44.01. Good. So if you do this calculation and then you multiply it by 100, what should you guys get?
$27.28.
Yeah, 27.3, like what we got. So that's how we got this right here. And this is just the percent composition, the way you guys learned it in workshop. So now we're going to move on to water. How many moles of hydrogen do we have?
2.
2. And how much does it weigh?
1 gram.
Yeah, exactly. Good. And how much does water weigh?
18.
Yeah, 18. Yeah, point something. I don't know what it is. But then if you do the calculations right, you're supposed to get 11.1%. So these are the percent composition of this whole. Okay, so now that we got that, the next step that he did, so we know that we have, what was it in the problem? 14.2, was it of carbon? I don't remember the problem.
Carbon dioxide, I think.
Carbon dioxide? Okay, so we have 14.2 grams of carbon dioxide, right? And we already know that 27.3% of that is carbon, and that's what we want to find out, right? So you're going to divide this by 100 because that's how you get the percentage, like we did in the past problem that we did right now. Okay, and someone gave me what you get here for carbon. Switch colors.
3.88.
Yeah, 3.88. Awesome. And what about, okay, now we have 8.7 grams of H2O, right? And what are we going to multiply that by? What do you guys think? Yeah, 0.111, because we just divided this. So we could get the grams of hydrogen in H2O. And what do you guys get there?
.97.
Yeah, 0.97, exactly. Okay, cool. And now, since we have 10 grams of this compound right here that we find out what it is, what do you think we're going to do with these two values in order to get how much oxygen we have?
Add them.
Yeah, we're going to add them. And what does that give you? Should give you like 4 point something.
.85.
Yeah, there you go. And what are you going to do with this value to the 10 grams?
Subtract it.
Yeah, you're going to subtract it. Guys, be confident. You guys know your stuff. Trust me. Okay, so then you should get 5.15. I think that's what it is. Yeah. So as you can see, these are relatively close to the percentages of your answers, right? So what we're going to do is we're going to just multiply each one by 10, each one of these answers by 10. And the reason for that is because all of these need to equal 100%. And if we multiply by 100, that's not going to give it to us. So let me just erase this.
Wait, can I ask why we added the 3.8 to the 9.7?
Yes, because
0.97?
Oh my gosh. Yes. Okay. So we added these two together because remember we have 10 grams of the compound of this mysterious compound that is made up of carbon, hydrogen, and oxygen, right? So we already know the values for carbon and hydrogen. So in order to find out what's missing, we just added these two up and then subtracted it by 10. Does that kind of?
Okay. Yeah, that makes sense.
Oh, okay. Okay, cool.
Yeah.
Okay, so now we just multiply this by 10, and this should be the answer Dr. Alexander gave you guys, which is 38.8%, 9.7%, and 51.5%. And the reason we don't multiply by 100 is because if we did, it wouldn't give us 100% in total. They should give you 100% total.
Just want to like add something onto what Claudia just said. Another way of seeing it, since we normally, when we're going from percent composition to empirical formula, we usually do it over 100 grams. Since we have 10 grams here, the easiest way to do it is to divide 100 by the total amount of grams that we have here, which is 10. And since that gives us 10, that's what we multiply as our factor to the rest of the carbon, hydrogen, and oxygen. Any questions? Does everyone understand how we got this?
So off of what you just said, Jeremiah, had it not been 10 grams, would you have multiplied by something different?
You would have had to multiply by something different.
Okay.
But luckily, Dr. Alexander loves us very much because he doesn't want to see us in pain. So he gave us 10. Or at least I hope it was on purpose. So any other questions?
How do we find the empirical formula for that?
So actually, the empirical formula, once we have this, is really simple, luckily. Like these percentages, you can just put them in, you divide them. Actually, before you divide or anything like that, you can just take these numbers right here. Oh, that was bad. You could just take those numbers right there, divide by the smallest one, which is the 0.97 from hydrogen. And then from there, multiply until you get your whole numbers and you're all good.
So you divide that by 0.97?
Mm-hmm.
Right.
Any other questions? Concerns? Problems?
Do you guys want to do a stoichiometry question?
Please.
I know a lot of my students had that had that trouble. Let's do one. Sorry, Claudia. Down. All right, let's do a stoichiometry question. I'm making this off the top of my head. Iron oxide. Iron 3 oxide. If I got 7.2 grams of that, give me something else to react with iron oxide. Let's do hydrogen
Sodium
gas.
sulfate.
All right, good suggestion. Sodium sulfate. I got 6.2 grams of that. When we react that, what is our limiting reagent? Okay, cool. So how we do this is obviously convert those into formulas. So iron 3 oxide is what? Like what's a formula for iron 3 oxide?
OH3.
Fe2OH3, perfect. And then sodium sulfate is what? All right, Na2SO4. Great answer. So basically switch these first ones. So that's going to be NaO, Na2O plus Fe SO4. So Fe2SO4. So yeah, we got that. Now we just need to balance that, make sure it's all good. I think that's right. Sound good? And from here, we can do as we did before, convert this to moles, so grams to moles, and then moles of A to moles of B, and then moles of B to grams of whatever. Do you guys need me to do this? Or you guys, kind of have the hang of it once I give you guys a little push? All right, let's do this. Okay. So iron 3 oxide, we need to convert this from grams to moles. How do I do that?
By multiplying by the molecular mass of the compound.
Okay, so we use molecular mass. That's 7.2 grams of iron oxide. So grams to moles. We wouldn't multiply because grams are supposed to be on the bottom. We take the molar mass of that bad boy, convert from 1 to, let's use sodium oxide. So that's 1 mole of iron oxide to 3 moles of sodium oxide. And then we can stop there. So that's how you would solve that one. Just plug in molar mass when you find that. Same thing for this side. Again, 6.2 grams over molar mass equals to 1 mole. That's a 3-to-3 ratio, so that's 3 moles to 3 moles. Cool. Everybody got that?
Wait, how did you get the last ratio for iron? 3 and 1.
Oh, well, we look at it here, right? So we got for every 1 mole of iron 2 oxide, we have 3 moles of sodium oxide. And same thing for here, for every 3 moles of sodium sulfate, get 3 moles of sodium oxide. Make sense?
You wouldn't compare it to the iron sulfate?
You can, but you don't have to. So remember, when you're doing these limiting reagents, you can take your choose between the 2 products. As long as we're comparing it to the same products at the end, then it's fair game.
Oh, the same one.
It's the same way.
Can you explain question 6 from the 5th set of study questions?
Okay, can you read it to me?
Yeah, I put it in the chat.
Sounds good. When copper oxide reacts with hydrogen gas at high temperatures and use this data to determine. Okay. Okay, so let's try to break this down. So copper oxide. Ooh, is that copper 2 oxide? Do you know?
Yeah.
All right, we'll say it's copper 2 oxide.
Mm,
It doesn't
or
say
it just
copper.
says copper.
no, it's
Ooh.
copper.
All right, well, let's say it's copper 2 oxide, right? That CuO reacts with hydrogen gas, which is H2, at high temperatures, making copper metal and water vapor. Cool, that's a single replacement. Single replacement reaction. We know that we start off with 10 grams of this bad boy, and after the reactions, we get 7.99 grams of that bad boy. Cool, so step number 1, we need something that we can work with. So my tip, probably get moles. So convert grams to moles, Does anybody know the molar mass of copper 2 oxide? Cool. That's 79 grams, or 79.55 grams per mole. And then copper is 63.55 grams as well. So convert that to moles. That's 0.55. That's 0.215 moles. That is also 125 moles. So we can see that they're about the same ratio. So that means if I produce 1 mole of this, that means I had to use 1 mole of this because, same ratio. So yeah, that's let's see, and use a percent composition of mass. Okay, yeah, so composition by mass of copper oxide. We know that's a 1-to-1 ratio. And we know that all of this is balanced. So we can just use composition by mass. So we know for sure that it's copper 2 oxide. And we know for sure that it is Well, yeah, that's all you would need to do. Is, that's all that like it's given right now. Just remember that there is, for every 1 copper, we use 1 mole of copper oxide, which makes it that. Does that make sense?
Yes, it also asks for the percent composition. So how do you get that?
Okay, well, if this is our formula, then we can also work backwards. So we can find the molar mass of this formula and say that the molar mass is 17.55. And if that is, let me do it right here. So if 100% of our compound is equal to 79.55, how much does copper contribute? And copper is 63.55. And we set up that proportion. So just multiply and divide that bad boy. And you should be getting something like around 79.8 grams, or 79.8%. Copper, you would do the same thing for oxygen. I'm guessing it's going to be something like 20.2%. So yeah, once we find out that this is our actual formula, then it's easy to convert into percent comp.
Okay, thank you.
So that concludes, we are at 6:30. That concludes our time. But if you guys need to have any more questions, if you guys want me to stay, I can stay. But as of now, the review session is over. So you guys have a good day. If you guys want to jump off, if you want to stay on, then that's okay with me too.
Jonathan.